Yes, sir.
Yes, sir.
Okay. Okay. Hi, my name is Ram, and so I'll be handling this week 5 week live sessions. Okay, and let's wait for Vishal to join. Okay, and once Vishal joins, we'll start the session. And but let this be clear. In this session, we will be discussing the only the week 5 contents, especially the activity questions on the practice assignment. Okay, and apart from that, if you have like any questions from the contents of week 5, right, that we can discuss. Okay, is that okay? Is that fine with you all? Hello, am I audible?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay, so that is okay, right? The agenda is clear.
Yeah.
Yeah. Okay. Okay. And one more thing, like, so since I'm like starting from week 5, and if I missed anything from week 4 or like from previous part, right, or if I make any mistakes, please correct me. Okay, between. And okay, so let's start.
Yes.
Okay. So how does it how does it normally go for you? So does it go like we will straight away go into the questions and then we discuss those activity questions, and then or how does it go?
We
How does
discuss.
Yeah.
We discuss the activity questions one by.
Okay. Okay. And then we move on to the practice assignment.
Sir, generally we discuss the activity question, but in the previous week we first discussed the concept and the concepts were not clear. So we first discussed the concept, then we went to the questions.
Yes, sir. First of all, focus please little bit on concepts and then the activity questions.
Yes, ma'am. I mean, there are few of us who might have few problems in understanding the concepts of week 5.
Okay. 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 So like discussing the concepts in sense, like, do you want me to go from A to Z, or like how does it go?
I mean, for me, it's like I didn't understand the part where Sir wrote that A minus IB in R into e to the power I theta. That form, I did not understand that part.
Okay. 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 So that okay. The graphical representation of the complex number, that thing, right?
Yes, sir. Graphical
Okay. Okay.
representation.
Okay. 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 So other than that.
Other than that, I mean, what is the, I mean, conjugate, sir, by conjugate, is it means that conjugate is something which is, which will be in 90 degree, which will be at a right angle to the given complex vector or something like that. Conjugate, what is conjugate? That part also.
Yeah. Okay. 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 That part we'll discuss. Okay. What else?
For me, only this. I don't know for others.
Okay. 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 So that all that which you talked about, that's from the first lecture, right? Right.
Yes, sir.
Whatever you talked about, that is from the first lecture, no?
First week.
That is from the first lecture of the
Yes,
first
sir.
lecture,
First
right?
lecture. Yes, sir. Yes, sir.
Yeah,
First
okay.
lecture. Yes.
Okay. 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 So we will start by that. Okay, we'll start by your doubts. Okay. So the first thing is, if I answer what is, yeah.
And one another small thing that we generally know that I, that is this imaginary number, these things does not exist. So how can we multiply a number by I and represent it in a graph? That part also. I mean, concept. I mean, the concept of that. If you can please explain a little bit of that, that would also be helpful.
Okay. Okay. Okay.
Sir, it would be helpful if you could go through all the concepts briefly.
Yeah. Yeah. Okay. Okay. Okay, I'll try to do that. So give me a second. I just connect my whiteboard so that I will show something.
Hello, sir. Your
Yeah.
voice is not clear.
Is it clear now?
Yeah, it's better now.
Okay, okay. Okay, so the first thing is, okay, what I'll do is I'll go through the lecture notes. Okay, from that I'll try to explain. Okay, will that work for you?
Yes, sir.
From the
Yes,
lecture
sir, yes.
notes, I'll try to explain.
Sir, you can discuss the necessary concepts of each lecture and then
Yeah.
discuss the activity questions.
Yeah. So that's what. So to discuss the necessary concepts, I'm saying that I'll go through the notes which was given to you, right?
Yes,
Yes,
sir.
sir.
Yes.
Yes.
Slides. Okay, I'll go through that and then like I'll explain. Okay.
Okay, sir.
Yes. That would be also.
Hello,
Yes.
sir. This is Bharat. Am I audible?
Yeah, you're audible.
Yeah, sir. Good morning. I have few concerns that I thought I would raise here. Sir, the lecture videos are actually not intuitive. Uh, I mean, like we are just going through the formulas. We are not able to at least I am not able to understand the relativity. There is no motivation on why I'm learning that particular concept. So what can be done with this actually? Because I'm already on a weak linear algebra foundation, meaning the max 2 concepts were actually was not of that quality, and we had already raised this issue. And on top of that, MLF, I thought it will actually be reinforcing what I learned, or it will actually clarify what I learned as part of linear algebra max 2. But that's not the case. It's so very dry. I'm not able to understand the connection between the concepts at the start. A lecture after lecture, it is working out of the concepts without any understanding or without any motivation. So I didn't know where I can raise this concern. So I thought I would use this particular forum to raise this particular concern. Because a classic example is eigenvalue, eigenvector. Without even understanding how eigenvalue, eigenvector is related to the 4 fundamental subspaces, I can't move further with SVDs and PCS coming in the future. And with this kind of a foundation, I will not make a good data scientist. I'm sure about that one. So what can be done with that? So is there any forum where I can escalate this? Because I mean, like with the first 4 weeks, this is the kind of foundation that I'm getting. I'm really concerned about the subsequent weeks that I'm gonna look at. So what can be done with that? What is your suggestion?
So one thing is that be patient. Okay, be patient. See, the way you learn, right? We always complain that okay from the starting that okay we were learning all this stuff and then like where will be implementing it and all, right? so like one thing I'll say from my experience is if you go through the lectures and then like if you like see you there'll be certain part which you understand, there'll be certain part which you won't understand, right? Like let's say using matrices to solve for the unknown values, okay, or the Gaussian emission method, which helps us find these unknown values very easier, right? So these are those equations or the equations that could be appearing in real life, okay, like the equations, the 3 equations with 3 unknowns, right? All that it be appearing in real life. So that part is kind of like apparent to us, it's like easier to us, but the other part which you're talking about, the SVDs and the eigenvectors and or the eigenvalues, right? Be a little bit be a little more patient, okay? As you go on, right? As you go on to the other courses, you will understand how this is like a very basic, okay? Even though you do not understand the applications part of it, if you're able to understand what's happening there, okay, then you'll be able to catch up. It's like what I feel. Okay, so do not worry about it. And if you have any questions on this, you can post it on Discourse. Okay, so from there we'll take it forward. Okay.
No,
And
sir. My question is, see, if I have any specific questions, I can post it. The point is, I'm not understanding the concepts, or I'm not able to understand the intuition behind it, because linear algebra is all about intuition. So if I'm not able to build intuition by going over the videos that is given by IITM, there is no point. And if I actually have to refer to Gilbert Strang, or if I have to go to 3 blue, 1 brown kind of videos to understand, then there is no point in me wasting time in looking at the IITM videos, correct? And from what you said, it is all actually going to be programs, but it's all going to be intuition, or what I have to do with the problem. It's all about how I am actually seeing that particular problem. End of day, I'm not going to do row echelon or Gaussian reduction of the matrix that is given to me, the 150 by 150 or 650 by 650 matrix. So it's all going to be Python programs. But if I don't know what program I have to do, then what is the point? So to understand what program I have to do, I have to understand the internals, right? I have to understand the concepts. If I don't understand how eigenvalue or eigenvector is related to the 4 fundamental subspaces, how eigenvector is related to column space, or how eigenvalue is helping me doing the matrix multiplications or whatever that is, then there is no point. I'll not be able to solve the problem at all. How do you expect me to raise this particular concern in discourse? Do you think it will actually get addressed? And if I'm actually waiting patiently, I mean, like, the course will go further, and I'll be adding more agony to what I already have. So we are already talking about Hessian, we are already talking about SVDs. The SVDs have already come. And if I'm waiting patiently, tomorrow SVD will come, day after tomorrow PCA will come, and I'll sit with the same understanding that I have right now. That is my real concern. That's where I was patiently waiting for 4 weeks. I patiently waited for 5 weeks. I don't see a point where the course is actually changing course. I still see sir taking a rough sheet and working out the formulas and all that. But there is no intuition building. I don't understand the background. I don't understand the reason behind eigenvalues and eigenvectors. I'm not able to relate it to the 4 fundamental subspaces. I'm not able to build on top of the concepts. That's the very point that I'm trying to say. And we are already in quiz 1 now, this weekend.
Yeah, so this like course is more of a theoretical like thing. So I guess from eigenvector and eigenvalues, maybe from the next week when PCA will come, you'll be able to know why we are calculating. So maybe the intuition part will be clear from next week and coming weeks. So that is what this is more totally a theoretical thing. So you have to bear with us for this course. And from the next course, when the MLF practice and theory will come, you'll be having all of coding and all stuffs. So whatever you are reading, so maybe you'll be applying in the next courses. So, but this is totally a theoretical, like all maths and all. So many times people generally feel like they are not able to connect this. So, but it's fine.
No, even Max, where is the relevance? I don't know whether you are really understanding my concern. I'm sorry about stealing the time.
Bharat, so like, okay, one thing I understand is you're not able to relate to what you have learned in the previous weeks and then like build on top of it, right? It's not more about the application. It's more about like you're not able to find the intuition of like why we are doing it and like how we are doing it based on what we learned previously. Is that your question mainly?
See, the point is every concept that we are knowing is related to each other. Where is the connection? You're not able to. I'm not able to understand the connection. I've already learned about column space. Is column space or 4 fundamental subspaces for that matter is related to eigenvalues? Definitely they are related. Diagonalization of matrix, definitely they are related. You're not able to give me that connection. Where is that connection? Every concept that I have learned in linear algebra till today is related to eigenvalues and eigenvectors. Have you brought in that connection to me in the lecture videos that is dished out till today? If not today, when will you be able to give? You are not even able to refer to the concept that that I studied in Max 2, and you said, see, this concept you studied in Max 2, and this is the extension concept that we are doing right now. Eigenvalue is an extension of some concept, right? You should have told me that particular concept that I learned in Max 2, and you should have told me, so this is a concept that you learned in Max 2, and this is how we are extending it to eigenvalues or eigenvectors or diagonalization. That relevance, that connection is not there at all. Formulas after formulas, if I'm learning, tomorrow I'll forget the formulas. Formulas is going to be of no help to me. But if I understand the connection, if I understand the relation, I'll be able to apply it. Why are we not able to bring that intuition, or why are we not able to bring that connection, is what my concern is all about. And I seriously don't know where to raise this concern. We have raised this concern in Max 2, and I don't find an appropriate forum where I can raise this concern. And that's the reason why I felt I wanted to open this up right now. I'm seriously concerned about MLF. If my MLF is not proper, how do you expect my MLP or MLT will be proper? This is foundation. I need to know my foundation very, very clearly. Only then I can establish that foundation in MLP and MLT. I'm kind of surprised when you say just pass through this MLP and MLT will make more sense. How will it make more sense?
Bharat, this is Muthu. Actually, I also have the same concern. It's a good thing that you voiced out, but I didn't.
Yeah, please, guys, please. Only then people will know the intensity of this particular problem.
Yeah, I don't know whether
I am facing this issue.
To answer to your question right now, but they have to really think about how to make the connection, how to move away from theory to practice, and all that. So that would really help. Otherwise, what I'm studying, and first week I'm forgetting in the third or fourth week, and already as you said, one is here.
Sir, here one thing, sir. Sometimes when mathematics teaching is done, whether it is related to the actual practice or not, math has to be taught in a totality. So you cannot tell that what is the connection now.
True.
Right? You cannot miss one thing because it is not connected to MLF. Eigenvalues, eigenfunctions are the extremely difficult topic because I know I'm physics lecturer, quantum mechanics related things. Only thing what I felt is that a little bit fastly teaching is done, like sir is writing on the paper in the class instead of like other courses where PPTs are already made and then fastly is going on. So here that connection is a little bit missing. Otherwise, you cannot point out that it is not directly connected now. Show me now like that. Math is always like that only. You have to learn.
No, sir. Just for example, I mentioned that it's just not eigenvalues, eigenvectors. The course all through. Tomorrow, if SVD and PCA, if you are not able to bring in the relevance, I mean, like, we will not able to understand the background of it. So eigenvalue, eigenvector is just an example, just to emphasize what I'm trying to say. That's all.
Okay.
So can we do it any better is what my concern is all about. Okay, can we do it any better? So now that I'm raising this, and I have a fellow of my other friends as well raising it. So my request to Ram or Abhinay or I mean, like, whoever we are having as part of MLF, can we make it any better? Because this is, if we are going to continue this way, then it's not happening.
Bharat, I have one doubt. Can I add something? Or earlier they recorded, and some other course for some other course they recorded, and they are matching now, because introduction is one way it is there, and later lecture is coming from some different channel and something like that. Like for earlier NPTEL course videos is clubbed up, or now specifically for this course videos sir is making, sir. That is my doubt. Maybe that is where the link is not matching up.
Yeah, the videos are made specifically for this course, that is for sure. Okay. This is not from NPTEL. Okay. And okay, I understand. So I kind of got like what you're trying to imply, Bharat and others. So yeah, I like
Just one point is actually we are not trying to get the solution right now today, but please think about it. That's all our question.
Yeah. So I understand, and the thing is, it's not going to happen within a few days, or like I don't think even it can happen in 1 week or so. There needs to be tremendous effort that needs to go into this. So basically maybe the structure of the videos should be changed, I guess, or maybe the interlink between those, or some additional content should be added, and that's not going to be easy, but we'll try to we will like we'll try to do something about this. So yeah, we'll try to add some content. We'll try to add some content, be it the videos or like something else. Okay, such that we'll try to incorporate this connection between this, and then like okay, the overall course structure, right? Why we are doing this, and then like how the next step is gonna like the bridge, right, across weeks and across concepts that we are going to try and that we'll try. Okay, and like even that might not be good, but the thing is, whenever we release that content, right, we expect your feedback, and then like based on your feedback we'll move forward. Okay, so is that okay?
Yes, sir.
Yeah.
And Ram, if you want me to put this as a in this course just as a follow-up, because now that we have discussed this in this particular meeting, if you want me to put this as a record in discourse, I can do that as well, so that we look for follow-up.
Bharat, this is Puneet here. Am I audible?
Yeah, go ahead, please.
Bharat, I really respect you bringing this up. You have spoken.
Hello.
The same problem. Yes. Hello.
Yeah, Puneet, go ahead. Sorry, you broke in the middle. Yeah.
Okay, I am on a bad connection. So firstly, you spoke up for us. Thank you. We are all facing the similar problem. And I think the recourse was that we did speak to JK sir, we did speak to the class committee, and they are looking into making changes in the courseware. Secondly, Abhinandan sir, the other instructor, he is now covering the concepts in these live sessions. So we do the concepts all over again. That's what we were requesting Ram sir, to just cover the concepts, help us understand the relationship to practical applications, and then go into problem solving. If that's okay with you, or we can Abhinandan join us in this session and explain how we can take it forward.
Yeah, live session is also perfect. Fine.
Right. So that's what we're doing now. That's what we had recommended, that we start with the concepts. We spend about half the class doing concepts and the other half doing the actual activities and problem solving.
Even
Can
after
we try
learning the
that?
lectures, after learning the lectures video, I was able to solve the questions of week 4. But when I joined live session and I studied on MIT lectures, I was able to grab the concept. So I think we should do more effort.
Yes, Manish, agreed. We are trying to do that in the live sessions, and maybe after quiz 1, we'll increase, instead of having 2 sessions a week, we'll try to make it 3 sessions. Maybe have a one session of concepts. So.
Yeah, Puneet, thanks for acknowledging. Even for Max 2, we spoke to JK, we raised this issue, but I don't know what happened, but somehow we were able to cross through and come to MLF, and we are facing the similar problem in MLF right now. See, my only concern is, after spending 4 hours of watching the videos that IITM has provided, we have to spend extra time on the live sessions and the other sessions, right? So what I'm trying to say is, if live sessions is what is practical, then let's go ahead with it, because we are already spending 15 hours for a particular course, and this is just getting piled up on to whatever time we are already spending. And being a working professional, it is actually completely impractical, and we are working on very, very tight timelines. So that's my only concern. So I can very well spend time on live sessions if that is really helping me in understanding the concepts, and I would actually ignore the actual videos if this is how it is actually going to be. At least if IITM tells me that, okay, this is how the videos are going to be, then I'll forget about watching those videos and I'll look at live sessions. Whenever Abhinandan sir or Ram sir is actually conducting the live sessions, I can go ahead and watch that. Wow, I don't have to waste my time in looking at something which is actually not, I mean, like serving me any purpose for that matter.
Yes, sir.
So that is my only
Videos
concern.
with length also 30 minutes like that it is there. Each one, many videos.
Yes, we also felt that the videos were directed towards solving problems without explaining the concepts. Okay, so let's try this. Let's do a session today. Let's see how this helps us. We have quiz 1 coming, and this is for week 5. So maybe we can redo this session next week also. All right, Bharat, thank you much. Thanks a lot. Let's keep on Discord. All right, for quiz 1.
Okay, yeah. So all your concerns are like will be addressed, and Bharat, yeah, please post that in the Discord so that you can ask for a follow-up. Okay, and then like you can know like what's gonna happen regarding the issue. All right, and if others have like similar problems, you can just reply in the same thread instead of creating a new one. Okay, and we'll move ahead to week 5.
Thanks, Ram. Sorry for stealing the time. Thank you.
Yeah, it's okay. Like we are also students, so yeah. Okay, so right. Yeah, so one thing I want to say is, okay, no, forget about it. So we have this complex matrices, right? Before that we need to be discussing this complex numbers, correct? And so again to discuss this application of the complex numbers, it's not so straightforward. Okay, so it is applied in like in this machine learning, of course, and it will be applied in like some high level studies, okay, like the quantum mechanics and others. Okay, so yeah, the applications are like not very much intuitive, but we can visualize it. We can see what this complex number is, and then like go about it instead of like maybe we might not completely understand the applications of it, but we can understand what a complex number is, and we can get intuition of like what it is. Okay, and let me just try to do it. Okay, so you're able to see the screen, right? You're able to see the screen?
Yes, sir. Yes, sir.
Yeah. So every complex number, it has an real part and an imaginary part. Okay. So the A plus IB is the general way in which we represent a complex number. Okay. Where A is the real part and IB is the imaginary part. Okay. So how do we? Yeah, again the reasons of like the applications of it we'll be discussing later. Okay, so not asking about it, but the visualizing part and the mathematical part of it, if you're not able to understand any step, you can stop me and then ask. Okay, and this is the complex number, right? And then like the way you represent it, I as many of you know, it is square root of -1. Okay, I is like this. So we have this A plus IB, right? And the way you can think it of is like kind of like x comma y in the 2D plane, right? We have this A comma B. Okay, so you can think of it in this manner. This A will be represented. A is the real part, right? As I told. And this B will be the imaginary part, so that is in the y-axis. Okay, so what we do is we go for this A units of length in the x-axis. So this is, let's say, A, and this is B. So the point of this A plus IB will be representing here. Okay, and this actual length will be the length of this or the magnitude of this complex number. So how do you find this length? It is just square root of x square plus y square, right? So it's basically square root of a square plus b square. Okay, and the other thing which others were talking about, right? That r e power I theta. Okay, So this theta is this we are representing in terms of a comma b, right? And we know that there is this other representation, right? The cylindrical representation is the angular way of representing. So that is, we have this magnitude, right? Square root of a square plus b square. That can be considered as radius of the magnitude, or whichever you want to call. So that is called as r. And the angle with which it makes with the this complex number makes with this x-axis, right? So that is called as theta. So this theta will be equals to, it is this tan theta, right? It is equals to b by a, right? Okay, and the way, so this is b by a, and this so the way, yeah, this is b by a, and we have this, we can represent this complex number as either a plus ib or r e power I theta. Okay, so this theta is the angle with which this complex number makes. Okay, when we draw a line from origin to the complex number. Okay, so that will be the angle, that is the theta. Okay, and the other one is the conjugate of it, the conjugate which you're talking about. The general idea of conjugate is when we multiply complex number a with another number, it will result in a real number. Okay, so this should be having the same magnitude as it. Then that will be this. Then that will be the called as the conjugate of it. Oh, no, let's not denote it by a and b. We'll denote this complex number as c1, and this will be this conjugate is like c1 bar, right? Which we generally represent. So the c1 into c1 bar, it should be equal to the magnitude of it. So which is nothing but a square plus b square, right? So this particular number, if we multiply complex number with another number such that it will result in the magnitude of that complex number, then this complex number is called the conjugate of this complex number c1. Okay, so for this particular case, we have the magnitude as a square plus b square, right? The distance from the origin, a square plus b square, and we have this complex number as a plus ib, correct? Now if you multiply this with a minus ib, what will it result? It will result in a square minus b square, right? The formula. So that is nothing but a square minus I square b square, which is equals to a square plus b square, correct? Which is nothing but magnitude. So this means that a minus ib is the conjugate of a plus ib. Okay, and the conjugate of the two. So and a plus ib will be the conjugate of a minus ib. So that is the reason in the lectures, whenever the professor talks about conjugate, he just replaces this imaginary part, if at all there is, with the sign of it, he will be replacing. That is a plus ib. A plus ib's conjugate will be a minus ib, and a minus ib's conjugate will be a plus ib. Okay, is this okay?
Yes, sir.
Okay.
And it's like the transpose in real space, right?
No, not exactly the transpose. The transpose.
No, I'm telling the like analogy. It's like
yeah, the thing is, I cannot understand like the intention behind your analogy, but I hope it makes sense to you. Okay.
Yes, sir. Yes, sir.
Okay. So yeah, this is what, and let's say we have a real number a itself, right? Without having any imaginary part, the conjugate of it will be a itself. Okay, since it does not have this imaginary part, so the real part will itself be the conjugate. Okay, so this is all about this complex numbers. Okay, and the way this part, is it clear?
So sir, can we represent any real number in complex number?
Yeah, so you can represent any real number in the complex number as I told, right? Okay, so let me just clear this.
So, sir, what is the difference between real and complex then?
Yeah, the complex number can have this imaginary part.
No, sir.
I
Suppose
is
we have
there,
a point 2, 3, then
you have
it
point
will be
2,
got.
see, it's 2, 3, that is in the xy plane, right? This is x and this is y, right?
Yes, sir.
And that is not a, and that cannot be represented here. As I told, you are talking about real numbers, now how to represent the real numbers in this.
But sir, we
this
can
complex
represent the
number
2,
plane.
3.
Huh?
Directly on 2 axis, we can directly represent sir 2, 3.
See, 2, 3, we can represent here, but that means that this is equal to 2 plus 3b. Sorry, 2 plus 3i. Right? So this, if you're representing it by, let's say, 2 and 3, this is 2 and this is 3, then this means that this is a complex number 2 plus 3i. Okay, that is why see, there you'll be representing two different values, right? The x coordinate and the y coordinate, right?
Then sir, what is the difference? Means whatever we learned in week 2 or week 3.
So the difference is the x coordinate corresponds to the real part,
Yes,
and
sir.
the y coordinate corresponds to the imaginary part. Okay.
So sir,
And
whatever
one
we
student asked, like, can we? Okay, let me just clear this and then I'll answer you. Okay, so one student asked, like, can we represent the real numbers in this as a complex number in this plane? We can do as I told the real numbers will not have imaginary part, right? So basically they all fall under this x-axis. So let's say we have this
Sir,
5.
can I come in once?
Yeah.
I think his doubt is 2 and 3 are real. Why are writing 2 plus 3? Sir, we are asking doubt.
See, the thing is,
yes,
this
imaginary
2
part,
and
real
3.
part, both are real parts only. 2 plus 3i. 3 is real, 2 also real.
Yes, sir.
But when you add it to I, it will become imaginary. Just it is a representation of a coordinate system in a different way.
Means it is only difference is only for representation.
Yes, obviously. Representation, easy method of calculations will come.
So
if
suppose
you take a complex number method, that is a way of doing some of the calculations easily.
So suppose we have y is equal to
only later when you understand the applications, not at the situation of definition. You can't understand why, what is the use. Later, when you get into the simplifications part and you use these complex numbers in some other parts, then you'll understand, okay, this is the use of taking real part and imaginary part like that.
So okay, means use of this part is only for simplicity of calculation.
Yes, obviously. Initially, it is made for simpler calculation, and later it is applicable to many areas. It went complex numbers.
Okay, thank you, sir. So means whatever we learned in week 2, suppose we have pair in form of x, y. So for that we have to predict y if we have given x. So can we represent those points in like this?
Yeah, you can represent like x, y coordinate you want to represent. Suppose x, y is there. Suppose the distance from origin is square root of x square plus y square. Right, sir?
Yeah.
Now the same x, y, if you present x plus iy and x minus iy, if you multiply both of these, then you'll get x square plus y square. That is the meaning of that.
Okay. Means for prediction also we can use this.
Yes. It is a way of getting some other things in a different way, more easier way. That's it.
Okay, thank you, sir.
Okay, so we'll move ahead on this. The complex number part is clear, right? Okay,
yes,
so yeah, and let's move ahead to the next part. If you go by this, it's gonna take like some long time. So we know this linear combinations of vectors, right? Normal vectors, and the linear combinations of this of this complex vectors. We have this we have the C1, C2, and so on, right? They're those C1 and so on. They're like real numbers. Here this constant itself, they could be complex numbers. That is, they could contain this imaginary part also. Okay, Is this clear what we're talking about when we talk about linear combinations of the vectors, right? Okay, of the complex vectors. While we talk about linear combinations, we multiply them by constants, right? That is how you get this linear combination. And in that linear combination, the constant itself can be a complex number. That is, it could contain the imaginary part. Is that okay?
Yes.
Okay, yeah. The next part is this important one. Okay, the inner product, and based on this, we'll be defining this Hermitian matrices number. And what do you define by this inner product? Okay, the inner product, the inner product is kind of like finding the magnitude of a vector, right? You know this dot product, right? Dot product of a vectors, right? So x dot x, it gives a magnitude of that vector, right? So unlike the x dot y, so it is dot product of two different vectors. Similarly, similar to that, we have this inner product, and if you multiply the vector by itself, then it will be giving the length or the magnitude of the vector. Okay, yeah, we are talking about complex, of course, in this particular case. Okay, so the way you get that length is just like you do for the normal vectors, x transpose into x. Okay, so and then okay, so no, this will be for the real vectors, but for this but for the complex vectors, directly multiply it like that, then that could be 0. So that's why we will not be doing it. We'll be defining it in a different way. Okay, so for the complex vectors, right, the inner dot product of two vectors x dot y, where x and y both are complex vectors, then that will be equals to the conjugate of the x conjugate transpose multiplied by y. Okay, so this conjugate, right, the conjugate of a vector. Yes, explain this. How do you find this conjugate of a vector? So it is just like the vector has, let's just say the vector of n dimensions, and then it has this, just say ai plus ibi and so on, an plus ibn, right? Okay. So this could be this one vector, right? Xi. Okay. Now the conjugate of it will be nothing but ai minus ibi and so on, an minus ibn. As I told, we just need to change the sign for this imaginary part. The remaining everything else will be the same. Okay. So once we do this, we need to do the when I talk about xi bar transpose, then this will be this column will become the row a minus ega, so a minus bn. Okay, I hope that part is clear. Okay, so when we have these two matrices, like when we're going to find this inner product of x dot y, right, we need to find this conjugate of x and then transpose it. Then we can multiply it by y. Okay. By doing so, we'll be able to convert this into single dimension. Okay. The overall purpose of this dot product is converting the multi dimensions into a single dimension, right? So that we'll be able to find that the value or length. Okay, here also we'll be converting that to a single dimension, but here it won't be a real number. It won't be a real number. It could be a complex number also. Okay, is this clear what I'm talking about? Am I making sense?
Yes,
Hello?
sir.
Okay. So yeah, the thing is, one thing that could happen is the intuition and the understanding from me will be different from the intuition and understanding from yours. Okay. When I talk about some things I might assume that you know this, and then like I might skip it. Okay. And some things could be like very much pretty evident to me, and which might not be evident to you. Okay. So you could like stop me anytime. Okay, and I'll try to explain you in a different way. Okay. And the dot product of the inner product of this x dot y is not the same as y dot x. Okay, that is illustrated in the example. To do this, you can as I don't know, you just need to find this to do the inner product. I'm just reiterating. You just need to find the conjugate and then transpose that particular conjugate so that it become before it will be this 1 by n, right? Now it will be becoming, sorry, before it is n by 1, right? Now it will be becoming 1 by n, and so that when we multiply this the conjugate transpose with y, we'll be getting a single dimension. Okay, the single dimension complex number. Okay. So as I talked about the length of the complex vector, it is similar to this magnitude of the magnitude of the real vector which we talk about. It is nothing but the inner product of that vector with itself. Okay, x per transpose into x. Okay, this is the length of the complex vector. This is exactly similar to what we talked about, that a square plus b square, right? That is for a single number. Sorry, that is for one complex number. Since a vector it has so many complex numbers, we do this inner product with itself to find the length of the complex vector. Okay, the length of complex number and the length of complex vector is clear. Is it clear?
So could you please
one
repeat
more
that
question,
again?
sir.
Huh?
In real world, sir, x transpose x was giving the length. Okay.
Yeah, x transpose into x gives the length. Yeah.
But here x conjugate transpose of x is giving the length squared.
Yeah, correct.
Okay, sir.
That is what. So as I don't know, it is exactly similar to that real vector magnitude which we do. That x transpose into x, right? Since we cannot directly multiply, since that will not give the actual magnitude, we will be doing this conjugate and then transpose. After that only we will be multiplying with x. Okay, we will not do this x transpose into x. We do this conjugate of x transpose and then multiply by x. Okay.
So here in this case, it would be the 1i case. It would be 1 into minus i, 1 minus i dot product of 1i, right? And that is how you get root 2 probably.
Yeah. Okay. So let me just do that. Okay. So we have this 1i, right? 1i. This is x. This is xi, or let's just say x. So what will be the conjugate of it? 1 minus i. Correct. What will be the transpose of it? X for transpose will be 1 minus i. We'll be converting this column to the row matrix kind of thing. Okay, x bar transpose. Now this x bar transpose into x equals to 1 minus I into 1. Okay, sorry for bad handwriting. Now this will be equals to 1 minus I square, which is equals to 2. Okay, since this is the square of it, the magnitude will be the root 2. Okay.
Yeah, thank you, sir.
Yeah. Okay, so let's just move ahead. And these are some properties kind of thing. Okay, which I don't think we need to discuss too much there. Okay, this we could check that out for yourself, and the professor has explained in detail there. Okay. So here when I mentioned now this C, right? whenever we have a constant here in this week 5, do not think it as a real constant. Okay, it could be the complex number. When I mention C, that could be some A plus IB form. Okay, that is why X dot CY is not equals to CX dot Y. Okay, here C and C conjugate in this second one, right? Second one we have directly C, and in third one we have the C conjugate. As I told, both are different. Okay, and okay, this conjugate transpose is what we talked about there. A star, which we have done, that the X bar transpose, right? Or like the X transpose bar, whichever one, then that is called as conjugate transpose. This leads us to the next definition. Yeah, the Hermitian matrix. Hermitian matrix. A matrix is called a Hermitian matrix if A star equals to A. That is the conjugate transpose. If it is equals to the actual matrix, then that is called as Hermitian matrix. Is it clear? Is it clear? What is Hermitian matrix? And what is this conjugate transpose and all? We have been talking about this conjugate transpose since we started this inner product. So this is clear? Hello?
Yes, sir.
Yeah, okay. So let us look at the questions there. Questions are not as scary as the lectures, I guess. Okay. The statement that inner product of two complex vectors is always commutative. Do you think it's true? The answers are like, do you think it's true or is it false?
False.
It is false, right? Yeah, as we have discussed, X dot Y is not equals to Y dot X. So it is not commutative. Okay. So if you consider vectors, the x1 is this real vector, and x2 is this complex vector. The denotation says that, and the n there shows the dimension of the vector. Okay, which computes with what is the square of the length of x1 and x2. So basically, what we're trying to do is we're trying to get the square of magnitude of x1 and x2. Okay. As we talked about, as we talked previously, for the complex vectors, we cannot directly multiply that by X transpose. Sorry, the X transpose into X. That will not give the magnitude for a complex vector, even though that gives that result holds true for the real vector. Okay. So if you look at the options, see, for the real vector, right, the conjugate is itself. So even though if there is a bar, or if it is not there, for the real vector, it does not make any difference, since it does not have the imaginary part at all. This part is clear? What I'm talking about? Hello?
Yes, sir.
Are you getting the intuition, or like which you're talking about? At least a bit? No? Are you able to visualize something? Okay. So this the first one as I told, for the x1, it does not matter whether that conjugate is there or not, because the conjugate is the same matrix itself. So x1 transpose into x1 is same as x1 bar transpose into x1. So that is clear, I guess. But for x2 it should be x2 bar transpose into x2. Okay. That conjugate is really important, since x2 is this complex vector. Okay, the vector consists in the complex numbers. So that is why option A and option B are correct. All right.
Yes, sir.
Okay. So the next one, A star. This is just a definition. The transpose of conjugate or conjugate of transpose, both are same. Okay. So this is kind of like easier, I guess. Okay, A star whole star equals to A, and these are simple definitions which are proved by the professor. Okay, and these two we have discussed. Okay, x dot cy is not same as cx dot y, where that c could be the complex number. Okay, so question number 5 is clear. Question number 5. Okay. So this conjugate transpose, right? The last one. Initially we can find the conjugate and later transpose, or we do transpose first and later the conjugate. Both are same. Okay. So since we have this one, and since this is the first question, the conjugate of one is itself, and even if you transpose it, this first element or the first position will not change. So that is going to be the same. But for 2i it's going to become minus 2i. So either the only correct option that could be there is only option 4. And this 1 minus i conjugate is 1 plus i. 2 minus 3 conjugate is 2 plus 3. When we transpose it, these two elements get interchanged. So this become 2 plus 3, 1 plus 3. So the option 6 is correct. Is it clear? Lecture 5.1.
Okay. Yes. Sir, question number 2 repeat, sir.
Question number 2. This one.
Option D.
Option D. Why is it correct?
Yeah.
Option D. See, for a real vector, right? For a vector consisting of these real numbers, the magnitude of the vector is nothing but transpose of a vector into itself.
Yeah. No, clear, sir. Clear. Okay. Okay.
Okay, so let us look at the second lecture. Okay, as we talked, okay, the Hermitian matrix is a matrix is a matrix for which the conjugate transpose of a matrix is itself. Okay, A star is how we represent this conjugate transpose. Then that should be equal to itself. Then that is called as the Hermitian matrix. Okay. To find a Hermitian matrix, it is kind of simple. Okay. The only thing is, if you see here, right, this 2 and 5, the diagonal elements, even though if you transpose it, their positions will not change, right? So what should happen is, for the diagonal elements, the conjugate should be itself. Okay. For the conjugate to be itself, the only way possible is if it does not have that imaginary part. As I talked, right? For the real numbers, the conjugate is itself. Okay. That is why for the Hermitian matrix, the diagonal elements will always be real numbers. Is it clear what I'm talking about?
Sir, can you tell me that how do we represent the matrix in the point form? Suppose we have matrix 2, 2 and 3, minus 3i.
We cannot represent the matrix in point form.
Why is it?
That point is only for the complex number, right?
Yeah, so suppose we have point 1, 2 and 2, 3. So suppose we have to represent these 2 points in the matrix form, then we represent in the column type, like suppose first column will be 1, 2 and second column will be 3, 4. Right, sir?
See, you mean to say like you want to represent this as the first one as 2, 0 and second one as 3, 3, 5, 0 and this one as 3, 3?
Yes, sir. Means my doubt is same, sir. Means can we represent or
you can see the thing is you can represent it, but that kinds of like complicates it. Okay.
What, sir?
Unless that is kind of like complicated for you if you see it for the first time. You do not know that we are trying to mean that it is a complex number, right? We do
no,
not
sir,
know that, right?
No, sir. But suppose we form a matrix from the points. Then sir, column size will reduce, na sir?
What? Can you repeat?
Sir, can you go on blank sheet, sir?
Okay. Yeah.
So suppose we have 2 points, 1, 2 and 2, 3.
We have 1, 2 and 2, 3. Okay.
Then in
So this is nothing but 1 plus 2i.
no sir,
plus 1
suppose
plus
in
3i.
if we form a matrix, then we will get 2 column matrix. The first column will be 1, 2 and second column will be 2, 3 in real form. Right, sir?
Like this?
Yes, sir.
Okay.
But sir, if we form a matrix in complex form, then we will get 1 plus 2i. First row and second row will be 2
No,
plus
no,
3i.
no. That is not how we do it.
That is why, sir, my
No,
doubt is.
that's not how we do it. Okay.
So how do we represent, sir?
In the complex numbers, the complex number is this will be this ai plus ibi, and then like a2 plus ib2, a3 plus ib3, a4 plus ib4. This how you represent. Okay.
But sir, suppose we have these 2 points, no? So 1, 2 and 2. So suppose we want to represent these
Okay,
2 points.
Abhinandan, huh?
Then how do we represent, sir?
How do you represent?
These 2 points.
Can I add something over here?
You want to represent this 1, 2, 2, 3, is it?
Yeah, sir.
See,
so can we represent or not, sir?
These are not points actually. These are like individual numbers, right? 1, 2, 2, 3. These are not points now.
But sir, we did calculations, sir, in week 2 and week 3 like this.
Okay.
Ram, can I add something over here?
Yes, sir.
Yeah. So see, who is asking doubt? May I know?
Yes, sir. Sir Harsh.
Yeah, Harsh. So the thing is, see, why we use matrices first thing to represent data, right?
Yes, sir.
So these columns are different. I mean, it depends on data how these will be filled. These matrix elements will be filled, right?
Yeah.
So in case of complex number, a complex number is complete with both its real part and complex part. So
Yes, sir.
don't assume they are different. A1, B1, which you represent in complex number, is a single unit. It's not a different unit, just like here, 2, 3, they were belonging to 2 different features, right? In our case, in previous weeks. But here, A1 plus IB1 is a single unit. It's not a separated unit.
So that is why, sir, my doubt is, sir, that can we represent these 2 points?
So this
Suppose
will be
we have given
represented
only 2
singly,
points.
right? So see, you have to understand when we use complex numbers. So complex numbers are used when we have something where we need 2 numbers to represent a single quantity. For instance, in case of electrical engineering, a current that you normally know, 5 ampere, 2 ampere, 3 ampere, it has 2 components. In when we are studying about magnetic fields and all, so there is a component which is in one direction and there is another component which is 90 degree to it. Now, how will you write it in a single number form? So there are 2 ways. One way is you write it in the form of A plus IB, where one represents in, suppose, horizontal direction, the other quantity represent 90 degree apart from that horizontal direction. Or the second way is you write the magnitude and then write the angle with it. Okay. So now this whole thing becomes a single number and it will take only one entry of that matrix. So if you have 4 currents, I mean 4 different values of currents, you will write it A1 plus IB1, then A2 plus IB2, A3 plus IB3, and A4 plus IB4, and each will be a single number. They will not be separated. So they will be written at one point.
So means, sir, according to you, if we have given only data, so we can't tell that means we can't represent, because we have to means in question it should be specified that if we have to reduce, suppose we have to compare pair, if you have to make a pair of 2 data, then only we can use complex number.
Yeah, so it basically depends on the data that you are taking, how you can represent it. So if it is representable by a single number, then you go for a single number. If it is represented by a case like current, where there are 2 components and you are representing it together, then it will be two numbers which are representing one thing only, but
Yes,
in
sir.
different
But sir,
dimensions.
yeah, but sir did not tell this, like, sir.
What?
But professor did not tell, na, sir, this thing.
Yeah, so see, this course builds foundation upon which you will be doing a lot of things. So
Yes, sir, because I
right
am.
now knowing everything is not I mean,
Yes, sir, I am
you
getting
cannot.
confused, sir, because suppose we represent 1 plus 2i and then 2 plus 3i, then we have only two vectors, and in earlier case we have four different points, 1, 2, 3, 2, 3.
So it completely depends on the data that you are collecting.
No, sir, data is same, but I think what we have to means, like you said, that means what we have to find, then only we will represent
Yeah,
differently.
so it
Na?
depends completely on data.
Okay, sir.
Okay.
Sir, I had a similar doubt too. So like in the real matrix that is given here, if it represented on a vector space, 1, 2 will be a vector and 2, 3 will be a separate vector. But in case of complex matrix, how will that be? Like there are A1 plus IB1 is like a one vector itself. So how will we represent like
Yes, I mean
I1
quantity
plus
of vectors has been reduced, na, sir?
so see, I1 plus IB1, which is written here, is not a vector, it's a number.
But it's like a x and y coordinate, right?
It's a xy coordinate, which is in total a number. It's not two different things. It is representing a single thing.
Hello, sir.
Yeah.
Can I say something?
Yes, go ahead.
It's like I think the main confusion is here that if we say any number 3, so the number 3, it is not on 2D space. If we say 3 comma 4, then it is on 2D space, x and y. But if we say only 3, then it is a point on the x axis or in a one dimension.
Yeah, so basically, see, a complex number contains all the real numbers. So when you are seeing 3, it is actually 3 plus 0i.
Yeah, and the complex number it is the if we say a plus ib, so a plus ib is a point on the complex space,
yes,
right? And which we are visualizing as 2D space for our understanding, is it?
Yeah, but it is a single quantity.
Yeah, it is a single quantity. Like in a real space, one dimension, we can point at only 3 on one dimension. It's like that, right?
Yeah, correct. Very correct. This is what I wanted to convey.
So could you give like an example of a 2 by 2 matrix and represent it in a vector space maybe?
Okay, so Ram,
Yes, sir,
can I share my
visualization part is
screen?
not clear, sir.
Yeah.
Because I can't visualize these two different things.
Yes.
Yeah, so see, suppose you have a condition. My data set is like this. I have two kinds of data, okay. So suppose I have speed, and then, okay, I have only one feature, speed, and I want to calculate distance from it. Okay, so suppose the condition and here I am saying I don't know those basic formula. Speed equal to distance upon time. This thing I don't know. Okay, and I just want to model a relation between distance and speed. So suppose for speed 2 there was distance covered 5, then for 3 there is 4, so and so. Okay, there are several points. So if you represent this using matrix, it will be simple. You will be doing this only, right? 2, 3. So there is no confusion regarding this, right?
Yes, sir.
Yeah. Now suppose I have a condition where I want to calculate displacement based on velocity. Okay. Now see, for displacement, again, let me take these points only. But now, since we know velocity has direction as well, right?
Yes, sir.
So speed can be represented only 2 kilometer per second. But here I have to represent 2 kilometer per second in north or in northeast, right?
Yes, sir.
So now how will I represent velocity? So if you represent speed, it will be like this. 2, right? So 2 0. Correct?
Yes, sir.
But if you represent velocity 2 kilometer per second in northeast, now you have to take it like this. Suppose this is north, this is east, then you are doing 2 kilometer per second like this in northeast.
Yes, sir.
Right? Now it will be having two components. One component here, this angle is 45 degree, right? So this is 2 cos 45 and this is 2 sin 45, isn't it?
Yes, sir.
Now I can write this as in complex form. If I want to write, I will write this velocity as 2 cos 45 plus I 2 sin 45. And this is together giving me 2 kilometer per second in northeast.
Yes, sir.
Got it? Now to represent this, I have two components, 2 cos 45 comma 2 sin 45. Got it?
Yes, sir.
Now how will I write this in matrix form? I will write it like this, 2 cos 45 comma 2 sin 45. And similarly for next case, 3 cos 45, 3 sin 45, right?
Yes, sir.
Now these two are single unit.
So,
or you can write 2 cos 45 plus I sin 45, 2 sin 45 and 3 cos 45 plus I 3 sin 45. Got it? Hello?
Yes, sir.
Hello, am I audible?
Yes, sir. Yes, sir.
Yeah, so you are getting this point, right? So it completely depends on the data that you are getting.
Means, sir, according to you, means if data itself has two categories, then we use.
So this velocity cannot be represented by a single number.
Yeah,
it requires two numbers for its representation, but it is actually a single unit.
Yeah. But sir, it has two categories, like in X direction and Y direction, like this.
Yeah.
Okay.
So
Clear, right?
this point is okay, but how will you represent like A plus IB on a complex plane?
Yeah, so this is like this, right? So this was complete A plus IB, where A is this 2 cos 45 and B is 2 sin 45.
Yeah, that is fine. It is dividing up into two components, but when you're making a matrix out of it, there are like four complex numbers, like A plus I, A1 plus IB1, A plus
So
A2 plus IB2.
in a matrix, what we know, this whole column represents a single characteristics, right? Which we call feature, right? And these rows represent different examples, example 1, example 2. So this is what it will represent. So this will represent, this 2 will represent speed for example 1. And 3 will represent speed for example 2. Similarly, here, this 2 cos 45 plus 2 sin 45 will represent velocity for example 1. And by example, I mean data of training set, first data of training set. And this will represent velocity for example 2.
Sir, that all is fine, but the matrix Ram sir drew, how will you represent that in a complex plane? That I cannot get, because there are like four complex numbers.
You cannot represent a complete matrix. So if you want to a representation like this, you can consider this to be like this. So this is 2 kilometer per second. So this is one thing, then 3 kilometer per second, then 4 kilometer per second. Okay, now all these components you are writing stacking together in a matrix. So you are writing it like this, 2 cos 45 plus I 2 sin 45, then 3 cos 30 plus 3I sin 30 plus 4 cos 60 plus 4i sine 60. Okay, so this is how you represent all the elements of a matrix on a single paper.
Means the number of column will be only one.
Yes.
Okay, sir.
Got it?
So we can say like the first element in this matrix is representing two directions in which that 2 kilometer vector is pointing towards.
Yeah, very, very correct.
Okay, got it.
Okay, got it, right? So I can stop sharing. Yeah, Ram, you can go ahead. Thank you.
Thank you, sir.
Okay. So we are at this Hermitian matrix, right? Yeah. As I was talking about, no, see, since this conjugate transpose should be same as this matrix, no, all the diagonal elements of the Hermitian matrix, it will be real numbers. Okay. Since for the diagonal elements, the transpose of it will be the same. The transpose does not change the position, and this means that the conjugate should be same as the diagonal elements, right? And that can happen only if the diagonal elements are real numbers. Okay. So that is why for Hermitian matrix, the diagonal elements will always be real numbers. Okay. That is one thing. All right. Is that clear? Yes, and sir. One other thing is, so we'll always have this conjugate of it, like 3 minus 3a, right? It is conjugate of 3 plus 3a. Okay, they'll be at this opposite position, so that when we transpose it, when we transpose it and then find the conjugate of it, it will be the same as the matrix A. Okay. The second part you need not worry, but the first part you need to take into account. Okay? The diagonal elements of Hermitian matrix will always be the real numbers. Okay, is that clear?
Yes, sir.
Yeah. Okay. So the next is the properties of it. Okay. The eigenvalues of this Hermitian matrix, it will always be this real numbers. Okay, and there is this proof also for that. Okay. This should, do you want me to discuss, or like shall we go ahead? Because the derivation part and all that, it's gonna take some long time. But if you've gone through lectures and if you did not understand a particular step in that, then you could like ask me directly. I did not understand a particular step. Please explain. Okay. Okay. So here, because like at the end, I just want to reiterate like what we talked about. Since lambda equals to lambda bar, we concluded that the eigenvectors are real numbers, because lambda equals to lambda bar can occur only if the number is a number is a real number. Okay. So the second one is this the eigenvectors of two different eigenvalues will always be orthogonal. Okay, the orthogonal means that they're perpendicular to each other, which means that the inner product of both it will be equal to 0. Okay, is this clear? The inner product and the orthogonality of two eigenvectors of two different eigenvalues. Okay, for Hermitian matrix.
Isn't that true for a real case as well?
No, that is not true. Real case in the sense.
In the sense, if it is, if I take A as a real matrix, not a complex one.
No. Then that's not going to be the case, because see, for X transpose into X2 equals 0, the only possible way is if that matrix, like if that vector itself is a 0 vector, then only the magnitude can be equal to 0, right?
So I'm talking the eigenvalues. So if A is a real matrix, and then I find the eigenvalues and try to find the eigenvectors, aren't those two eigenvectors orthogonal to each other in a normal matrix?
In a normal matrix, yeah, that need not be always the case. That won't always be the case.
Okay, because I assume that it is true for the real case as well.
Okay. So for this itself, like just again reiterating, for the summation matrix, the eigenvectors will be orthogonal for two different eigenvalues eigenvectors. Okay. And the just an example illustrating the same. Okay. And later we have this proof for this. Okay. And if you do not understand any part over here, then you can stop, or else we can just move in because we do not understand. Okay. At the end again here, since this lambda 1 is not equal to lambda 2, which we mentioned for two different eigenvalues, so x dot y should be equal to 0, which means that they are orthogonal. Okay. So here this part is like this part is important. If no eigenvalues are repeated, then the A is like diagonalizable. Okay, diagonalizable. Like we can be writing it. We can be writing it in terms of this eigenvectors, and then we can be representing it in terms of eigenvectors and the eigenvalues itself. Okay. For that we have this example over here. Okay, so here we have illustrated this A since A is diagonalizable, we just found A based on this eigenvectors columns, okay, and the eigenvalues itself. A8 and -1 are the eigenvalues there, and this 1 1 plus I 1 minus I minus 1, they are the eigenvectors corresponding to this 8 and -1. Okay, so that is the end of this second lecture. Okay, we'll discuss the questions now. Okay, so Hermitian, the Hermitian matrix in a complex space, right? A generalization of what real vector space? What is the answer for this? It's obviously symmetric, right? Okay, because as we talked about, the transpose of a conjugate should be the same as the original matrix. Now for the real vector space, when we talked about, the conjugate will always be the same vector. Sorry, the conjugate will be the same vector space, and the transpose of it, if it is equals to A, then we define it as symmetric matrix, right? So that is why the Hermitian matrix or the generalization of symmetric matrices. Okay, or else you could say symmetric matrix in a real vector space is a special type of Hermitian matrix where there won't be any imaginary numbers. Okay, imaginary values. Okay, so this one, Hermitian matrix are orthogonal and diagonalizable. The eigenvalues are distinct. This we discussed at the last part of the lecture. Okay, so that is true. The next one is this: diagonal elements of Hermitian matrix are real. This we discussed, right? The professor has mentioned a proof there too. Okay, the diagonal elements of a Hermitian matrix are always real because the conjugate transpose should be the same, and the transpose does not change the position of the diagonal elements, which means that the conjugate should be same as the original number, which will happen only if that diagonal element is a real number. Okay, so that's why it is true. Okay, and these two we have discussed in this lecture. Okay, the eigenvalues of a Hermitian matrix should always be real. Okay, because in the proof there we had that lambda bar equals to lambda. Okay, the conjugate is the same as the original number, which will happen again if only if it is a real number. Okay, the next one, the eigenvectors corresponding to distinct eigenvalues of a Hermitian matrix are orthogonal. Yeah, these two we have discussed. These two we have discussed. That is true. Okay, and the last one is all real symmetric matrices are Hermitian. Yeah, that is true. As I told, right, symmetric matrices are a generalized or a special type of Hermitian matrices where there won't be any imaginary part. Okay, where that I part will not be there, IB part will not be there. So symmetric matrices are kind of like special matrices. So symmetric matrices also fall under Hermitian category. Okay, so that is why it is true. Is this clear? Lecture 5.2, is it clear?
Yes, sir. Yeah.
Okay. So let me know, like, if I'm like discussing something fast, or like if you're not able to catch up with what I'm saying. Okay. Or if I'm slow also, you can just let me know. All right. So moving ahead. So here, there before we talked about Hermitian matrices, where the transpose conjugate should be same as the original original vector. Okay, then only that we call as this Hermitian matrix. For this unitary matrix, right? The condition is different. It is when this when the transpose conjugate it is multiplied with the original matrix, if it results in I, then that matrix is called as unitary matrix. If this U star U is results in this identity matrix I, then U is called as this unitary matrix. In other words, U star should be equals to the U inverse. The inverse of a matrix should be equals to this transpose conjugate. Okay. If that holds, then it's called as a unitary matrix. Okay. So in the real matrix, in the real vector space, we have this A inverse into A equals to I. What do you call that? Equals to I. What do you call that vector space? A inverse into A equals to I. What do you call it? Okay. What do you call that? I forgot about it. Can cancel? No. A inverse into A equals to I. Those are called as orthogonal matrices. Orthogonal matrices. Okay. Yeah. So these unitary matrices are similar to this orthogonal matrices. Okay. All right. So moving ahead. So if a matrix is unitary, that does not mean that it is Hermitian, and on the converse is also not true. Okay. So one other thing is, since this U star into U equals to I, right? The eigenvalues of a unitary matrix will always be equal to this the absolute value of the eigenvalues will always be equal to 1. Okay, this is exactly similar to the orthogonal matrices A inverse into A equals to I, where the eigenvalues will be either 1 or minus 1. Okay, that is the absolute value will always be equal to 1. Okay, this is clear. The absolute value mod lambda will always be equal to 1. Okay, I hope that is clear. Okay. And one other thing is, if you look at it, the modulus, right, or the length of the each vector in this unitary matrix, it will be equals to 1. Okay, if you look at this, the length or the length of the vector is 1 by root 2, 1 by root 2, I by root 2. This falls under one vector, right? If you look at it, the magnitude of it is also equal to 1, and the same goes for this I by root 2 and 1 by root 2. Here the cos t and sin t, the magnitude is equal to 1 because cos square t plus sin square t equals to 1. Similarly, the same goes for this the second column. Okay, for this second example in matrix. All right. So the other thing is, when we multiply a vector with a unitary matrix, right? Its length will not be changed. Ux will always be Ux length will always be the same as the original length of that vector. Okay. Okay, the second one we discussed, the absolute values of the eigenvector is always equals to 1. Again, similar to the Hermitian matrix, the eigenvectors corresponding to different eigenvalues are also orthogonal. Okay, so this part is like important. For Hermitian matrix A, we can find a unitary matrix U such that A will be equals to U star is lambda U star, where this lambda is this diagonal matrix. You know this diagonal matrix, right? The diagonal matrix will have this all the elements other than the non-diagonal elements will be equal to 0. Okay, so for a Hermitian matrix, there will always be a matrix, unitary matrix, such that this condition holds true. Okay. All right. So the proof for this it will be discussed in the next lecture. Okay. 5.3, is it clear?
Yes, sir.
Okay. Yeah.
Hello, sir.
Yeah.
Sir, a small doubt, not from 5.3, but what is the difference between the linear independence and the orthogonality? Is there any similarity between those, or are those totally different? I am a little bit confused about these two.
So first thing is they're like completely different. They're not the same. That's one thing. Okay, and like how they are different, it's like it's like when you say two vectors are like are like linearly dependent, right? That means that when we the linear evaluation of the two matrices, let's say we have these two vectors x1 x2, okay, which are like linearly dependent, which gives that c1 x1 plus c2 x2 will be equal to 0 for some values of c1 c2. Yes, illustrate that. We have this x1 x2, okay, these are like vectors. These are vectors, and then we have this c1 x1 plus c2 x2. If it is equal to 0, then this means that x1 and x2 are dependent, linearly dependent. Linear because the degree over here is 1. We are not multiplying x1 with itself, or like we are doing it. We are not doing that sort. We are just linearly adding it, and if that results in a if that results in a zero vector, right, then this will be called as linearly dependent vectors. Okay, but the orthogonal vectors is when x1 dot x2 it is equal to 0. that is kind of means that they're like perpendicular to each other. Okay. All right. So that's why this linearly dependent and independent on the orthogonality, they are not the same. Okay.
Okay.
Okay, so let's look at this 5.3. Yeah, I'll just remove this. I better remove the answers and then I'll just share again. Okay, as we discussed, the matrix is unitary if this is square matrix and has orthogonal columns. This is square matrix and has orthonormal columns. U star equals to U star equals to inverse. Why do you think the first option is wrong and then the second option is correct? First of all, is the first option also correct? Others? Do you think the first option is correct?
No, sir, it should be orthonormal, not orthogonal.
Okay,
orthonormal is a special case of orthogonal. Yeah.
Okay, yeah, and what's the difference?
So the norm has to be one, not more than one.
Which one? The norm must be one.
Yeah.
Okay, yeah. Okay, and this U star equals U inverse, that is evident, right? Because by definition, if U star into U equals to I, then only it will be called as unitary matrix, which means that U star equals to U inverse. Okay. Hope that part is okay. All right. So the second one, if U is unitary, if U is unitary, which of the following statements are true? U star is unitary. U star equals to A, that is always true. And columns of U form an orthonormal set, that is true. So yeah, all of these are correct. Okay. The third one, second question is clear, right? If you do not ask any questions, I will just be proceeding further, thinking that you do not have any questions.
How is the first one true? U star is unitary.
So we have this let's just try to do that. You know that U star equals to U star equals to I, right? Correct?
Yes, sir. If U is unitary, right?
Yeah. So and we know that U star whole star equals to U, right? This holds true for the matrix, correct?
Yes, sir.
So for the U star to be unitary, what needs to be true? U star into U star whole star should be unitary, right? This should hold true, no? For the U star to be unitary.
Yes, sir.
So, but then again, by the definition, U star whole star equals to U, right?
Okay.
So this means that this is identity. This we already know, correct? And this we know from the first lecture that U star whole star is equal to U. This holds true irrespective of what the matrix is. So that is why U star multiplied by U star whole star is equal to identity matrix.
Okay.
Clear? No?
Yeah, but is U star and U star U same, sir? I mean, are they commutative like that?
Yeah, for this case, yes.
Okay, okay, sir.
See, because U star U is like identity, right? So the ours also okay.
Okay, sir. Yeah.
Okay, the next one, the eigenvectors corresponding to distinct eigenvalues of in the matrix are orthogonal, as we have discussed previously. It is same like the Hermitian matrix. In this case, for distinct eigenvalues, both for Hermitian matrix and the unitary matrix, the eigenvectors are orthogonal. This thing, every unitary matrix is a Hermitian matrix. This is not true. All unitary matrices are not Hermitian, and the converse is also not true. All Hermitian matrices are not unitary matrices. Okay. And the last one too, we have discussed the eigenvalues of a unitary matrix. The absolute value should be equal to 1. That is, it could either be equal to 1 or minus 1. Okay. Shall we move ahead? Fourth lecture. Hello.
Yeah, go ahead.
Yeah, okay. Before we go there, right? Can I take like 5 minutes break? After that, we'll discuss. Is that okay?
Yes, sir.
Yeah, okay. Yeah, thanks. After 5 minutes, we'll be back. I'll be back. Hello. So let us resume. What we discuss. The next important topic is this diagonalization of Hermitian matrices. As we were talking, right? If you have a matrix A which is Hermitian, then we'll have a unitary matrix U such that A equals to U lambda U star. Okay, where this lambda is this diagonal matrix which has only this diagonal elements. Okay, and the proof for that is done initially by showing that any invariant matrix unit can be represented such that A equals to U to U star, where T is this upper triangular matrix. Okay, and since this Hermitian matrix is equal to its conjugate transpose for this particular Hermitian matrix, it will be this T will not only be upper triangular, it will also be lower triangular, which means that in total it is a diagonal matrix. Okay, and the proof for that is shown here. Okay, so this A equals to U to U star, right? Irrespective of what the A is, like whether that is Hermitian matrix or not, that is just Schro's theorem. Okay, and the proof for that is shown here, where this ZUB or the orthogonal or the vectors of this A are the normal vectors, like we will be converting that to orthonormal by dividing that with the magnitude of that vector, right? So by doing so, you'll be getting this orthonormal vectors. Okay, and by definition, orthonormal, since there is a special type of orthogonal, Z1 star U equals to Z1 star B equals to U star B equals 0. Okay, and by that, like once we have framed that, the professor has shown that U star A into U1, it will be equals to upper triangular matrix. Here in the upper triangular matrix, this lower triangular whichever we have, this will be 0, and this star element, right, which they need not be 0. Okay, that is the whole definition of this upper triangular matrix. Similarly, this we are done for the outer row, and similarly we can do that for B, which will be this 2 by 2. Okay, for that also we need to find this. We need to find this vector U2, unitary matrix U2, such that P star BP it result in another upper triangular matrix. So in total, we can represent this. We can represent this in total as U star in this manner: U2 star, U1 star, A, U1, U2. Okay. So this in total will result this entire upper triangular matrix, which is T. But for our case, we are talking about this Hermitian matrix, right? So we will show that for this. This is just another example of like finding that. Okay, here the part which was discussed is It was only the Schro's theorem, which is generalized for any matrix, not just for the Hermitian matrix. In the later lecture, it was discussed for Hermitian matrix too, where it is not just a upper triangular matrix, it is an entirely diagonal matrix. Okay, we'll discuss that lecture too, and after that we'll look at the activity questions. Since the 4 and 5 they are like directly related. Okay. So for a Hermitian matrix, as we discussed, U star AU equals to D, diagonal matrix. Okay. So from the Schro's theorem which was seen, U star A equals to T. T is this upper triangular matrix. A could be this any matrix. Okay. But for our case, this T star, if we just modify it for our case of Hermitian matrix, we'll be seeing that this T is this upper triangular matrix and T star is this lower triangular matrix, which means that and this T equals to T star, which can only happen if all the non-diagonal elements are equal. Okay, this is just like that. A equals to A equals to A star thing, but here what happens is on all the non-diagonal elements initially are 0, so that means that all the non-diagonal, the upper non-diagonal elements are 0, which means that the lower non-diagonal elements should also be 0. Only in that case this T equals to T star could happen. Okay, is this clear what I'm trying to say? One second. Okay, so since this T equals to T star, this also means that the diagonal elements, right? The diagonal elements are real. Okay, this part we have been discussing from the first lecture. When T equals to T star, the diagonal elements of the matrix, it should be real. Okay, this is an example for that. Okay. So for the real symmetric matrix, the corollary from the Hermitian to this, right? We have this any symmetric matrix. Symmetric matrix is similar to this Hermitian matrix, right? As we discussed, for any real symmetric matrix, we have this orthogonal matrix Q such that Q transpose AQ is equal to D, diagonal matrix. Okay, it's just similar to what we have seen there, except that we are trying to find the corollary for the real vector space. Okay. Okay. Any other questions in this? Any other questions until now? No?
I guess they don't have any question. So
Okay.
Ram, we can discuss the remaining portion maybe after quiz. That would be.
Yeah. So we will just go through the activity questions and then for the remaining we can discuss after quiz. Okay.
Yeah.
So as we so the first question which should be clear, I guess, for a Hermitian matrix, we can find a unitary matrix such that A equals to this BA B star, okay, where this symbol represents the diagonal matrix, okay, with the eigenvalues of it. So those values, so that A matrix it will have all the eigenvalues of A. Okay. And the next one is this. The spectral theorem shows that any Hermitian matrix is unitarily diagonalizable. Okay, and that too, that it can be found in the lecture there. Okay, so the next part is this Schur's theorem. Okay, in the for a given n-band matrix, it need not be the Hermitian. There exists a upper triangular matrix T such that T equals to U star. Okay, that is the Schur's theorem. The opposite also will be there, where we have this A equals to U star T U. Okay. The next one is this Hermitian matrix A. The spectral theorem dictates states that D equals to U star AU, where you use the unitary matrix. Here D is this diagonal matrix with real interest. Real interest is important because since that for this particular case, right, D star equals to D, since the D star equals to D, it will have only the real interest. Okay, it is not just an upper triangular matrix, it is also a lower triangular matrix. That is why it is called as this diagonal matrix. Okay. By definition, that's what diagonal matrix is. And this was mentioned clearly in the lecture. Every unitarily diagonalizable matrix, it is not Hermitian matrix, but every Hermitian matrix is unitarily diagonalizable. Okay, unitarily diagonalizable. That means that we'll have a unitary matrix U such that A equals to U star AU. Okay, whichever whatever we are discussing until now. Okay, and every Hermitian matrix is unitarily diagonalizable. That is true. Okay, the converse is not true, but this statement is true. Okay. So, any other questions? And until now, until these lectures. Oh, sorry. Yeah. Any other questions? If there are no other questions, then we can wind up this session. Okay.
Sir, can we have any revision session before the final lecture?
Yeah, we do have this revision session. We have one on Saturday. Yes. Right?
Yeah.
Go through yeah. We have one on Saturday.
Yeah, we'll be having revision session, I guess, day after tomorrow.
Yes.
Announcement is sent or not? I think it must have been announced by now.
I'm not sure about announcement, but it is there in the calendar.
It's 2 p.m. to 4 p.m. Saturday.
Yeah. Okay. So thanks everyone. And if there is nothing else, we can close the session. And yes, so that query, right? You can just, as Bharat said, you can just post your queries there, and maybe we will try to like do better, okay, to make this course understandable. Okay. Thanks everyone.
Yeah, thanks a lot everyone for
Thank you, sir.
participation. Thank you, Ram.
Thanks. Yeah, bye.
Thanks everyone.